Welcome to our Chapter 13 lecture video. Today we're going to talk about solutions. A lot of today is going to be a bit of review and a little bit further on what we've already talked about. So we're going to define what a solvent and a solute is. A solvent is what the majority of a solution is. A solute is what the minority of a solution is. We've talked about homogeneous versus heterogeneous in terms of a whole bunch of things. Today we're going to talk in specific about solutions. A homogeneous solution is a solution that fully dissolves in itself. A heterogeneous solution would be like oil and water that does not fully dissolve in itself. Concentration dilutions are going to be somewhat new. We're going to have some calculations that are pretty straightforward, similar to, PV1 equals PV2. We're just going to have M1V1 equals M2V2. So molarity is going to be a big thing here. We've introduced this, but we haven't focused on it yet. And then we're going to refresh on solubility and introduce something called ion effects or colligative properties. And so the first thing we're going to get into is homogeneous mixtures. A homogeneous mixture is just any mixture of solutions that is fully dissolved. So, seawater is a solution, blood is a solution. A solution can be a mixture of gases and liquids, solids and liquids, liquids and liquids. Technically, you can have gas, and solid, but we're kind of beating it over the head, so to speak. So we have a solvent, which makes up the majority, or at least 51% of the solution, and a solute, which makes up less than 50% of the solution. If we have a solution containing mostly water, where water is the solvent, we call this an aqueous solution. Aqueous solutions are very important to most of nature and biology, and so we define them as such. So here's just an example of table 13.1 of all the different types of solutions we can have. We're mainly going to deal with, the liquid solution, so gas, liquid, solids dissolved into another liquid. But we can have solids like, the example here, or if we take sodium and potassium, mix them together at a specific ratio, we get a solution. Gases are another very common solution industrially. We've kind of talked about them in terms of the ideal gas law, but we haven't defined them as such. Here's just another table with common solvents. So here we have our non-polar solvents, things that would dissolve fats or oils. Here are our polar solvents, things that will dissolve ionic compounds or be miscible in water. So remember, miscibility is the solubility of two different liquids. And so if we have two miscible solvents, we'll have a homogeneous solution. Just to remind us of what happens when we actually dissolve a solid, an ionic compound's the easiest to think of because we have this electrostatic interaction between sodium and chloride. We learned from chapter 12 that essentially all intermolecular forces are electrostatic in nature. It's just how big is this dipole? We can have a partial minus and a partial positive that can come and break up this full positive and full minus. However, we're going to need a whole bunch of molecules for the partial positives and partial negatives to break up the electrostatic interaction of the full positive and the full negative. And so we have what's called saturating a solution. Once we have as many of these molecules in solution, as many ions that can be surrounded by whatever the solvent is, we call that a saturated solution. Once we have more than the amount of crystals or whatever material we're dealing with that can be dissolved or fully surrounded by the solvent molecules, that solid will just fall or settle to the bottom of whatever container we're working with. So we have solubility. Solubility is how much of something can dissolve at a given temperature. So at 25 degrees Celsius, we could put 36 grams of sodium chloride into 100 grams of water. Like I mentioned, if you put as much material or solute into a solvent as possible, we call that a saturated solution. This is the maximum amount of solute that you can put into a given solvent. This is a function of pressure and temperature, but since pressure doesn't really change much on Earth, we typically just think of it as in terms of, temperature. An unsaturated solution would be something that has less than the maximum amount. A supersaturated solution, which is pretty rare, is a solution that has more than its traditional maximum amount. If you were to do this, without any specialized techniques, increasing the pressure, increasing the temperature, and then alleviating to some lower conditions. So here we can see a specific example the book gives for a supersaturated solution. What we want to pay attention to is that the way that we saturate or increase the solubility of a gas, a liquid, or a solid is all different. Liquids and solids tend to behave the same, where as you increase the pressure and increase the temperature, solubility increases. However, gases typically have the inverse behavior, whereas you increase the temperature and increase the pressure, you decrease the solubility of a gas. And so here there was a negative pressure and that increased the solubility of the gas. So solubility, we talked about this in chapter 7. We had the common phrase, like dissolves like. Polar things dissolve polar things. Non-polar things dissolve non-polar things. Anything that's an ion is going to be polar. The larger the molecule, the more non-polar it's going to tend to be, just, statistically. So we have electrolytes and non-electrolyte solutions. Electrolyte solutions are anything that conduct electricity. You have to have ions to conduct electricity. If you don't have any ions, even a polar molecule like sugar will not conduct electricity. So you need to have these dissolved ions, positive and negative isolated charges, not just partial positives and partial negatives. So if we have a polar solution or covalent compounds in a solution, we're going to have a non-electrolyte solution. If we have ionic compounds in solution, then we will have an electrolyte solution. So we already mentioned this. Solubility varies with temperature. It typically has a positive relationship with temperature. However, we see here that cesium carbonate does not have a positive, has a negative. As you increase the temperature, the solubility decreases pretty fast at first, but then it kind of tapers off. And so every compound will have a different solubility parameter with temperature. So some increase linearly, some increase exponentially, some have a lower slope than others. And so it all depends on the chemical, the intermolecular forces. You don't need to memorize any of these, but you could have to use a chart. So if I told you how much potassium chlorate could I dissolve at 70 degrees Celsius, I'd find the potassium chlorate curve, I'd find 70 degrees Celsius, I would go to that temperature and then figure out, I can dissolve 30 grams of potassium chlorate for 100 grams of water. The next thing we're going to talk about is recrystallization, or crystallization, depending on how you want to view it. But recrystallization is just taking some solid, dissolving it in some solution or solvent, then causing it to reprecipitate in a more pure state. So the book gives one of the most simplest ways to do this. I'll give another way to do this that's more common in the laboratory. But there are hundreds, if not thousands, of different ways to crystallize or recrystallize different materials. And so the book gives the simplest way, where you elevate the temperature of the solvent. This allows you to dissolve more of that solute. It elevates the saturation point. You then allow the solvent to cool, and it will reprecipitate more pure solid. Now, sometimes this can lead to a supersaturated solution if you're careful or lucky. Most of the time, this leads to recrystallization. Another way to do this is to take a solvent that has only partial solubility for your solute, dissolve as much of that solute into that solvent, and then find another solvent that is miscible with your first solvent, but not miscible with your solute, and then that will cause it to crystallize. An example is a lot of ammonium salts are very soluble in isopropyl alcohol or rubbing alcohol, but not very soluble in water. So you can dissolve the ammonium salt in as much isopropanol as possible. Then add water. The isopropanol is more soluble in the water, so the water and the isopropanol would rather interact due to their intermolecular forces, and the ammonium salts are left to crystallize out or become a pure solid. Now, we've already talked about the solubility of gases and solutions, but just to reiterate, they increase with increasing pressure. Solubility always increases with pressure. If there's more force forcing things together, they're more likely to interact. So pressure always increases solubility, but temperature increases the solubility of solids and liquids, typically, and decreases the solubility of gases. So we want to reduce the temperature and increase the pressure to maximize the solubility of gases. And so a great example of this is soda. Soda's typically always at the same pressure unless you have it sealed in the bottle and you shake it up, then you increase the pressure. But then you're forcefully removing some of the gas. That's a different kind of situation. And here we have two different sodas, one poured from a hot bottle, one poured from a cool bottle. The one from the hotter temperature is going to have less solubility for the gas, so more of that gas is going to readily leave the solution. Again, pressure increases the solubility of everything. There's always exceptions, but I can't think of a single exception where pressure doesn't increase the solubility. We had that example of cesium sulfate, I believe, where the solubility was decreased by increasing the temperature, but that's a very rare case for solids and liquids. Definitely the case for gases where the solubility increases as we reduce the temperature, or the solubility decreases as we increase the temperature. But Henry's law is kind of the formal definition or mathematics for why gases and liquids and solids are more soluble at higher pressures. So concentration is something that we've addressed in the lab and a little bit in some of the challenge questions where I give you the moles and the volume, or I ask for the grams per liter. Concentration is just some amount of something per something else. We typically talk about concentration in terms of molarity. That's the most common concentration for chemistry. However, you can have grams per liter, grams per centiliter, grams per milliliter, kilograms per liter, meters cubed, whatever. Ultimately, all we need to determine the concentration is the amount of solute referenced in the numerator divided by the amount of solvent referenced in the denominator. And so one way to do this is mass percent. This is most common for everyday things. So if you buy vinegar, you buy it by 5% mass to water or 10% mass to water. If you buy it from Home Depot, maybe you get it at 35% mass to water. And so everyday people, engineers, physicists, they really like to put things in terms of mass percent. Engineers are what make the world run. Physicists, chemists, biologists, we devise a whole bunch of things, computer scientists as well. And then the engineers actually produce it on scale so that the rest of the world can enjoy that technology. So mass percent is just the mass of solute, the thing that you're dissolving, divided by the total mass of everything. So the mass of the solute and the solvent. So percent mass. By mass of the entire thing, this is how much you're actually getting. If I have 100 grams total and I have a 5% mass, well, that means the mass of the solvent is 95 and the mass of the solute is 5. You have 5% relative abundance of the solute. So we can just convert everything into grams, use our dimensional analysis, and make sure that everything makes sense. Obviously, you're never going to have more than 100% mass. It just doesn't exist. You can't have more than 100% of a real thing. Statistics you can, but that's, conventions. So here would be an example. So given this sample, it contains this much CO2 by mass. How much mass of CO2 is there in total? Not by percentage, but just in total. So we know there's this much volume. This is the percentage. We have the density. We have all the things we need to convert. We can just think of this as grams per grams, 8.5 grams per 100 grams. Or we can just treat it as the decimal. Same thing. Here would be our dimensional analysis. We're going to start with our liters. We need to convert to milliliters because that's what our density is in. Once we have that, we can multiply by our density. That will give us just grams. Then we can use grams of solution versus grams of CO2 to cancel everything out. Because the solution is water, we just need to know the density of water, not the density of CO2 or something else. It's just the density of the solution. At the end of the day, we'll get our grams of CO2. Pretty straightforward. The most common unit that we're going to use is molarity. We've experienced this in the lab. We haven't used percent mass in the lab yet, but we've used molarity, 6 molar versus 0.1 molar or 12 molar. 12 molar is twice as concentrated as 6 molar. 1 molar is 10 times as concentrated as 0.1 molar. Pretty simple. We just consider the moles of the solute divided by the liters of the solution. So this is the final amount of volume because, the solute that you dissolve into the solvent is going to add some amount of volume. It might not be as much as the dry volume of the solute, but it's going to add some amount of volume. If you add, 5 grams of sodium chloride to water, the water is not just going to stay the exact same volume. It's going to increase by some amount
to position those sodium and chloride molecules between the water molecules. So here would be how we prepare a dilution, typically from a solid material. You put the amount of solids you want in there. You fill to some fill line. These are called volumetric flasks. They're very carefully calibrated. Unlike a graduated instrument that is graduated or marked at various different measurements, a volumetric flask is marked at one measurement that has very, very good accuracy. You can then use this as a stock solution and dilute that stock to, working solutions. So here would be an example. If we have 15 grams of sodium chloride and a liter and a half of solution, what is the molarity? First thing we have to do is convert grams into moles using our molar mass. Then we can take our moles divided by our liters. So molar mass sodium chloride, we want to divide by the molar mass to get to moles. Grams to moles we divide. Moles to grams we multiply. Then we can just plug into our molarity unit. Molarity is moles per liter. Moles per liters. That will give us molarity. So just the moles divided by the liters. Fairly simple. Things we've done before. Just a little bit more formalized. So we can use molarity in calculations. I essentially did this for you already where I gave you the moles and I gave you the liters. I essentially gave you the molarity unit in the last challenge question, but now we're going to actually formalize everything in just terms of molarity instead of how many moles and how many liters, as I did in the ideal gas law problems. So we have this many liters, this many moles. Moles times liters will give us mass or moles. We can then convert moles into mass. So here's our molarity. Here's our molar mass. We just multiply both of these so that we can get our grams. One thing we have to be careful about is with ionic compounds. So if we have 1 molar calcium chloride, it's true that we have 1 mole of calcium, but we also have 2 moles of chloride. So kind of with the, I think it was exam 1 challenge question, or no, exam 2 challenge question where you were given sodium phosphate and you had to figure out what the concentration or grams per liter of sodium ions were. Same idea. We still have to use our molar ratio or mole ratio when we consider ionic compounds because they dissociate. So very similar to our challenge question, just kind of simplified in terms of steps. Given the molarity of sodium phosphate, what's the molarity of sodium and phosphate? Sodium is going to be 3 times as much because it has a 3-to-1 molar ratio. Phosphate's just going to be the same as the molecular or the ionic molarity. So multiply by 3 to get 4.5 molarity for sodium, and the molarity for phosphate is just 1.5, like the given ionic compound, because it's a 1-to-1 ratio between sodium phosphate and phosphate ions. Solution dilution is one of the most common chemistry tasks that we do. If you get a job in analytical chemistry or even as a lab tech, this is at least 50% of your wet chemistry responsibility is just making solutions. Stock solutions are concentrated forms of solutions that you work with quite often. Working solutions are the diluted stocks that we can actually work from. So the way we do this is a simple dilution equation, M1V1 equals M2V2. Since the total amount of the total amount of stuff in there, the total amount of moles is not changing. It's just the molarity. Molarity times volume equals moles. So no matter what, on each side of this equation, we have moles as the units. If we're not adding any new compounds to it, we're just adding solvent, not adding any new solute. We're not going to change the amount of matter in there that we care about of the analyte. And so the volume will just change the concentration. So, like I said, molarity times volume is just moles. So we're just keeping the moles the same. We do not change the amount of material in there, just the amount of volume of solvent. Here would be an example of one of these type of problems where you're given 3 of the variables, have to rearrange and solve for the missing variable. And so this is just an algebra problem. We're going to divide by M1 to isolate for V1 and then plug in all of our variables, you want to make sure your units cancel out and you're just left with the correct unit. You shouldn't be getting liters if you're solving for molarity, but we're solving for volume, so we should have liters. Makes sense. And so, here's just kind of a visual representation. We take our stock solution that's way more concentrated, we add a little bit of that, and then we dilute up to a final volume. And so in this case, we added so much, we knew everything except for the liters, and so now we needed to figure out what volume did we need to fill to for that working solution. So just like all of our other chemistry where we can convert from one amount of material to another amount of material, we can use solutions and molarities to convert our stoichiometry problems as well. So given some amount or some volume of A, the molarity can convert us from volume to moles. Moles can be converted to moles via our mole ratio, and then we can use molarity again to convert from moles to volume. So just the same as the molar mass, we can now use molarity as a conversion factor. So if we have a certain amount or a certain volume of H2SO4, we know what the molarity is. We can multiply these together to get the moles of H2SO4. We then can use our reaction stoichiometry to compare moles of sodium sulfate to moles of sulfuric acid. We then can use the molarity of the sodium sulfate, or sorry, not sodium sulfate, that's the product we're making, the sodium hydroxide, to figure out how many liters of that sodium hydroxide solution needs to be used to completely neutralize the reaction. So, whole bunch of words for a little bit of dimensional analysis. We'll see that we just need, about 600 milliliters of sodium hydroxide solution, which makes sense since we have more moles of sulfuric acid than we do sodium hydroxide, and the mole ratio of sodium hydroxide is larger than the moles of sulfuric acid. So we could do this again with just a different setup. So in this case, now we have lead nitrate reacting with potassium iodide. In this case, 2 molecules of potassium iodide react with 1 molecule of lead nitrate. We could use our molarities, our mole ratios, and then our final molarity to calculate how many liters of Ki we need to finish off this reaction. We'd see that we need about 400 milliliters of potassium iodide solution. It makes sense for kind of the same reasons. We have a higher concentration of lead nitrate than we do potassium iodide, and the mole ratio is higher for potassium iodide than lead nitrate, so we should have a significant more volume of potassium iodide than lead nitrate. One of the last things we're going to talk about are colligative properties, or what I more simply refer to as ion effects. Ion effects are what is the effect of putting an ion in solution. The simplest way to think about it is that if I add sodium chloride to water, I'm going to increase the boiling point and decrease the melting point. So we ice roads because this reduces the melting point or reduces the freezing point. The melting point and freezing point are the same. It just depends on which direction you're coming from. If we reduce the freezing point or melting point, we have to have a lower temperature to cause things to freeze. So our roads will ice at lower temperatures if we add salt to them. Also, if we add salt to our pasta water, it will boil at a higher temperature. Not a very high temperature, but it can increase the rate at which your food cooks. And so essentially, whenever we add a non-volatile solute to a solvent, it will increase the range at which it remains a liquid. So the book calls these colligative properties. Most often they're called ion effects. Colligative properties refers to just the freezing point, depression, and boiling point elevation. But there are some other effects that can be generalized into ion effects. Typically, this occurs by adding ions. However, you can add covalent compounds, but it's much more common with ionic compounds that we see this rather than, adding urea to water to increase the intermolecular forces. No, we'll just add some sodium chloride. A lot cheaper, less stinky. And so for these freezing point depression and elevation questions, boiling point elevation, freezing point depression questions, we're going to use a quantity called molality. This is very similar to molarity, where we have moles of solute versus kilograms of solvent. Before we had moles versus milliliters, liters, or really just liters. Millimolar would be moles versus milliliters, but moles per liter is molarity. Molality is moles per kilograms. So this is more of a engineering and physics term that was developed for these type of calculations, as well as other calculations outside of chemistry. So if we wanted to calculate the molality, well, first we need to figure out how many moles we have. We can figure out what the molar mass is from the periodic table and divide by the kilograms of solvent. So using the molar mass, we'll figure out that there's this many moles. We'll then divide by the half a kilogram of water, and that will give us our molality. Molality is lowercase m. Molarity is larger case m. We're always going to use molarity. I don't even know if you'll see a molality calculation on an exam or final. It's absolutely on the homework. It's something that you should be familiar with, but for me, it's something that you should more see and be like, oh, okay, yeah, I remember that, rather than just having it in the top of your brain right off the bat. So we can calculate these. Here is the formula. I would give you these formulas for the homework. You're obviously going to have to look it up. But, delta is just the change of any variable. F is freezing. V is vaporization. So this would be, the freezing point depression. If we had delta T, V, that would be, or E, you might see in some textbooks to represent elevation, but typically it's going to be V for vaporization. What is the change in the vaporization temperature? So we just take the molality times the temperature, or the freezing point constant. And so we can calculate for this constant given these values. Pretty straightforward. Not something that we do very often as chemists. This is more an engineering thing. So make sure that all your units cancel out, because all we're looking for is a change in temperature, so degrees Celsius. So if we add this amount of solute to the solvent, it will reduce the freezing point by 3 degrees Celsius. This isn't a -3, it's reducing by 3. Okay, so same thing. So in here we have delta T boiling. Again, you might see vaporization or elevation. It really depends on the textbook. These are not super common calculations, but delta T of B, or of boiling, would be the change in the boiling point based on the molarity and the freezing point or boiling point elevation constant. So we can plug everything in just like we did before, and we can get some constant. We want to make sure that, everything makes sense. Now, using this constant, we can solve for a new problem. Given 1.7 molar ethylene, what is the, elevation of this boiling point? And so we could plug in all these values and find out that really the elevation is very minor, less than 1 degree Celsius. And so freezing point depressions are usually greater in magnitude than boiling point elevations. And this is because the difference in intermolecular forces from solid to liquid is less than the intermolecular forces, or the difference of intermolecular forces between liquids and gases. For a solid and liquid, we just have to overcome the intermolecular forces that fix everything in place. Whereas from liquid to gas, we actually have to break all of the intermolecular forces. So we're going to have much lower elevations than we do depressions in these type of problems. Osmosis is going to be the last thing that we talk about. It's not going to be too important to chemistry because osmosis is more of a biology or engineering thing. So osmosis is the opposite of diffusion. Diffusion is things flow from high concentration to low things. They diffuse out from the epicenter. Osmosis is things flow from low concentration into high concentration. And you need some type of machinery, some technology to actually cause this to occur. In biology, we have enzymes and different molecular structures that help this occur. Ultimately, what we have are semi-permeable barriers that allow things to flow through one direction, but not another direction. So in the body, we have these semi-permeable membranes that allow water to flow through them, but not ions. So there's a higher concentration of ions over here, and so it pulls water into this, semi-permeable barrier. It then can't flow back, and so it's trapped in there. Once you have so much pressure that's pushing against this membrane, water can no longer flow through it, and that would be called equilibrium. The flow through is equal to the flow out. There is no flow out, so there can't be any flow through at equilibrium. And this is just called osmotic pressure. If the pressure pushing back on this membrane, filter, whatever, is the same as the pressure pushing forward, you have no transfer of fluids. And so in this case, we're not having a transfer, but we let it equilibrate. This is the transfer. Eventually, the pressure that all these concentrated particles push against this filter is going to be equal as the force pushing these particles through this filter. That's what we define as osmotic pressure. That's basically when the osmotic flow stops. Very important to biology and aqueous flow chambers, but we're not going to deal with anything like that. So it's essentially relegated to true and false questions and book questions. We talked about a whole bunch of hodgepodge topics. Chapter 13 is very much the author's, well, we forgot to talk about this stuff, so let's cram it all into one place. We've talked about most of these things to some degree, but not all of them specifically. So the big thing is all the different types of solutions we talked about: solid, liquid, gas, liquid, 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 gas, gas, solid, solid. Those are all kind of new. Solvent and solute is kind of a new designation. Solute is the minority of the solution. Solvent is the majority of the solution. We did a whole bunch of different concentrations. The ones that you need to be concerned with are molarity above all else, then mass percent. And then if you remember molality, awesome. It's one of those things where if you see molality, you're more than likely going to be in a position where you can Google it, meaning it's probably not going to be on an exam or quiz. But molarity absolutely will be on every single exam that you will take from here on out. And mass percent is a fair question for this unit and the final. So we talked about dilutions. M1V1 equals M2V2. We're just changing the volume. The amount of material staying in there is the same, and so the moles will always be constant. Because molarity times volume equals moles, moles has to equal moles. All we're doing is modulating the volume and the concentration, not changing the amount of material. We have our ion effects, which we summated as freezing point depression and boiling point elevation. Essentially, you add a non-volatile thing or solute to a solvent, and it extends the range of the liquid. Basically, it maximizes the amount of time that material spends in the liquid state. Here are equations that you could solve for. You'll really only see this in the homework. And then osmosis. Osmosis, super important to biology. It's why we're alive. If we didn't have, osmotic pressure and these semi-permeable membranes, life would not exist as we know it. And so osmosis, super important to biology, but this isn't a biology class. So here are key topics. Really, you want to focus on concentration dilutions, and then, solvent, solute definitions, as well as homogeneous versus heterogeneous definitions. Solubility is something we already went over in previous chapters, so definitely be familiar with it. And then ion effects essentially relate to intermolecular forces. So again, a review of chapter 12, and then solubility, I believe, was chapter 7 or 9? No, chapter 7. So if you have any questions on any of these topics, make sure to reach out to me. Otherwise, I'll see you in lab this upcoming week.